So it's already 7:05, so I guess we'll start. And once again, thank you for all for joining in for this Astronomy Sundays event. So basically, Astronomy Sundays is a type of event where uh, usually we all members of Astronova and others from different colleges and universities across the globe join in for various state-of-the-art discussions on various topics like radio astronomy, any branch of astronomy in general, where we invite eminent speakers for us and they give a wonderful talk. So for today, we have with us Dr. Mugundhan V. So first, I'll tell what Astronova is. Astronova is the astronomy club at University of Calcutta in collaboration with IEEE societies and student branch chapters who organize online and offline events in the domain of astrophotonics, radio astronomy, astronomical instrumentation, space sciences, and astronomy in general. A bit about our speaker as well. So once again, thank you, Dr. Mugundhan, for accepting our offer. So Dr. Mugundhan V completed his PhD in astronomical instrumentation with a focus on radio astronomy through the integrated MTech PhD program from Indian Institute of Astrophysics and University of Calcutta. After a brief stint at Raman Research Institute, Bangalore, and University of KwaZulu Natal in Durban, he is currently a senior research engineer at the Onsala Space Observatory, Sweden's national infrastructure for radio astronomy. His interests are in antenna and array design, instrumentation, both analog and digital, and signal processing. So, Dr. Mugundhan will be speaking about very long baseline interferometry techniques, discoveries, and opportunities. I think I'll waste no more time, and yes, mic is open for you, sir.
Thank you. Let me just share the screen again so you can see if it is all fine. Is everyone able to see it? Oh, yeah, I think maybe now, yes.
Yes, we can see.
Okay, thank you. So I'll in general be speaking about what VLBA is and how it evolved as a technique from the time that radio astronomy originated as a separate area of research in astronomy. And I'll also try to cover on how the field has evolved since its beginning, and then how it has how the techniques and the instrumentation has evolved, and then which eventually led to imaging the black hole for the black hole for the first time at the center of our galaxy and at M87, and then also will give a brief outlook on what we expect to see from this as we go forward in time from now. And maybe in the end, like if people are interested in how to get into doing radio astronomy, and then we'll be maybe able to answer some questions also. But this would be and I've also structured the talk so that it is able to give a lot of historical viewpoints on how the development went in a certain way rather than a different way that it could have gone on, and what distinguishes radio astronomy and interferometry in radio astronomy specifically from doing interferometry in other areas of astronomy itself. Just a minute, sorry about that. Yeah. And then so as we all know, radio window presents one of the largest observing windows for us from the ground, extending from a few megahertz even up to far infrared sometimes, where you could there were experiments like Sophia where you could observe far infrared radiation from a moving platform on a moving telescope on a flight. But yeah, so this is the window in this the radio window in this picture is highlighted with the red things mostly. And once we go to far infrared and then towards millimeter wave frequencies and all that, the borders between radio and then optical sort of start coinciding, and you would enter into this regime called quasi optics, where your radiation is you're not talking in terms of waves, but rather you're talking in terms of wave fronts, but you're not talking completely in terms of having plane waves like you do in radio astronomy as well. So it's that's why it's called quasi optics. But that is an entire discussion. Probably I think you would have had some talks on that a few weeks back. But then going on and over this entire span of bandwidth, the element that we use primarily for detecting signals are basically antennas. The way they look may be different depending on what frequencies we are operating. So for at very low frequencies, people would typically be using dipoles, while at higher frequencies we would be using more like horns, and then maybe at even higher frequencies, depending on whether we want to detect power or whether you want to detect voltages, we would be using different types of coherent or incoherent detectors that are available to us. But mostly, like, I would restrict myself to, like, I wouldn't go as in this talk. We don't go as far as like far infrared or sub-millimeter wavelengths. So I would basically like restrict myself to millimeter wavelengths. So we would be in the regime of antennas mostly, and the signal that we expect to see from the sky is Gaussian noise-like. So when we just like point our antennas to the sky and we just try to like log the voltage signals that are coming from them, and if we try to make a histogram, it would resemble the shape of a Gaussian, which means that the process is completely random in nature. And the way we stumbled upon this is an interesting accident. So when Karl Jansky was building this huge antenna to measure the influence of thunderstorms and other terrestrial interferences on transatlantic communications, he actually like stumbled upon radiation from the Milky Way galaxy itself, and then he was able to like present this, like do this experiment again and again, and like when he noted the day-to-day differences between the time that he got to speak, he was able to infer that this did indeed come from a sidereal source, and then he was able to like present this results to both astronomers and engineers equally. And then this is a map made from Jansky's observations at approximately 20.5 megahertz. This map itself was not made by Karl Jansky, but then this was made using the data presented by Karl Jansky. So, but then here you can basically see, because the antenna itself there was like operating at 20 megahertz, the response of the antenna that it is seeing in the sky is like pretty huge. So, which is the reason as to like why the contours here are like so huge, and that you don't really see small. You see structures. You don't actually see sources. So then, and this could be attributed to the fact that Jansky was using this dipole-like antenna. It had a really large beam, and like typically you wouldn't be able to distinguish between between sources that are smaller than the beam as independent ones. And we would talk more about resolution and angular resolution in the coming slides. So. But then, like, once Karl Jansky did this, the person who continued on radio astronomy during the World War II era, when most other people like went to work on wartime efforts like building radars and other things, was Grotreber, who had his own 10-meter dish behind his house, which was built from scratch, and he actually like made uh, um, maps of the radiation at like three. Initially, he tried doing this at 900, close to some frequencies close to 900 megahertz. He did not see anything there because the radiation that he was receiving from the sky was suppressed by the noise in the instrument that he had, in the amplifiers that he had himself. And then he came to a slightly lower frequency around 300 megahertz, and there was not much he could see there also. Then he finally came to, I think, 160 megahertz, where he was able to measure radiation from the galaxy, and he was the first one to recognize that this radiation was mostly non-thermal in nature. Non-thermal in the sense, like, if we expect radiation that is thermal or is following black body distribution from Planck's black body distribution, you would expect it to have high intensities as the frequencies increased. But then here it was the opposite sense. So and then like this diagram that he shows actually is the location of. So when he has pointed his the beam's maximum towards the galaxy, he tries to give a picture of like where different sources in the known sky is at. So you can see that 331.4 degrees is like the right ascension of the galaxy, and then like you have Cygnus at almost 4 degrees, and he shows where the sun is and all that. And this was to sort of give a engineering picture of what you would see in the sky with respect to your antenna's location in the sky itself. And this was the map that he generated based on this. And again, here we see that you are not able to really distinguish between sources. So this sort of uh, gave the sort of like created concerns on the legitimacy of these maps that the radio astronomers were making, because most other astronomers were not really able to sort of make a connection between the maps that are shown in the radio wavelengths with what you would see from these from optical telescopes. So this sort of led to a quest to push observations to more high angular resolutions in radio astronomy as well. And so here, here you see, like when you have a telescope or any object, the maximum angular resolution that it is able to get is decided by two factors. One is the diameter of the telescope, and the other one is actually the wavelength at which you're operating. So optical telescopes, even though they have only like 1 or 2 meters in size, they would be able to like get close to millisecond resolution because they operate at a much lower wavelengths. While radio telescopes, even though they have like hundreds of, even though sometimes they have hundreds of meters of diameter, they would be able to like get only a few arc minutes of resolution at best. So this is because of this Rayleigh criterion. And but actually, like there are ways which radio astronomers have tried to overcome this basic resolution limit created by the physical size of the primary receiving element itself. And this led to so early on, like this wasn't like really realized by the radio astronomers that started off in the beginning. Although, and so there was sort of a push to build larger and larger the single dishes. And even now there are like some niche areas where large single dishes are like definitely useful. But then you get into the question of how large can you actually build things. So this was tried, and this was sort of answered in a different way, because like when people were working for the World War II effort, they got experience in radar and interferometry, and how you would be able to like add signals using different elements in the radar to synthesize a higher signal to noise ratio. So using this, they applied this problem in a reverse sense. Like instead of for transmitting with a high power, they thought of doing this in a case like where they'd be able to receive signals. And they also thought that if for example, like one is able to mimic what Young was able to do in his double slit experiment, you would also be able to like push resolution to a slightly higher limit, where instead of now the size of a single dish being a single dish or a single element uh, deciding how deciding your resolving power, it would be the separation between the two. So one of the earlier version of this sort of an so earlier version of this interferometer was the Seacliff interferometer, which was designed in Australia. So this was a radar which was overlooking the sea, mostly to like detect incoming aircraft, detect incoming aircraft as early as possible. But then you had so this was antennas which are mounted on top of as a cliff which was very close to the sea, and you don't have so many sites like that all around the world. But the way it worked was like you had a direct ray coming in from the source that is rising above the sea level itself, and then there is a reflected ray which is coming from the reflection of the radiation from the source from the sea's surface, and these two combine at a phase which is decided by the height above which you mount your antenna above the sea. So the Australian scientists were able to like detect sun, and in fact the first estimates of Cygnus A's size came from these interferometers. And they had a bunch of these interferometers, maybe two or three of them, operating along the coast, and they were even able to make very high angular resolution measurements of active regions associated on radio emission from active regions associated on the sun as early as even 1946. But a limitation of this is that you don't really get spots close to the sea as as common as you would have. So this proved like a sort of a limitation for how far you can like extend this application to for example to. So this again like is I think it is Bolton, like he's standing with the sea interferometer antenna, and then you've got fringes from Cygnus A. But then, like I said, this was again an issue like where you won't really be able to sort of do this experiment all the time, and then you also are limited by the fact that you can't like extend your baseline above a certain distance, because there are only like you could even if you have, even if Mount Everest was close to a sea, you could just probably have a baseline of 8 kilometers and not more than that. So which would in fact prove very restrictive if you're operating at a frequency like 10 or 20 megahertz, because 8 kilometers at 30 megahertz, for example, is just 1 or 2 arc minutes. So yeah, maybe around an arc minute is the angular resolution that you would get, which is not sufficient for you to like resolve many sources that we know of today. So then At the same time, there was a parallel development going on in England by Martin Rail's group. So here, instead of mounting an antenna close to the sea, this were mounted sort of close to uh, they were mounted on the ground itself, and then you had this phase reversing switch between one of the antennas. So this sort of like alternated the signal coming from one antenna, adding them in phase in one side and adding them out of phase in the other side. And then there was an amplify, and then the power from after this in phase and out of phase components were combined, were detected, and then recorded in the interferometer, and then this sort of produced these nice patterns. So one thing that you could see from the previous one to here is that the mean component of the power is like already removed. So which means that you are now sensitive only to components which are so in the earlier case you were sensitive to the total power added from both the antennas, but in this case you're here you're not sort of sensitive to the baseline, you're just sensitive to the radiation coming in from those components of a particular size or a scale, which is set by how the interferometers are separated. And then if we watch this closely, like one of the problems plaguing today's radio astronomy is radio frequency interference, which comes in because we are starting to have more and more transmitters which transmit in the frequencies that we want to observe. And multiplying interferometer can take care of some of it at a first level, because now you're not adding signals, you're just like multiplying them, and only signals that are correlated in both the antenna sort of gets recorded. So then, like we said here, both the Australians and the English are able to like detect discrete sources now. But then, how big or how small are these discrete sources is the next question that sort of plagued the radio astronomers at this point. So for this, an interesting idea which was proposed was by Cyril Hazard. So he came up with this idea called lunar occultation, where instead of using and making a large antenna on the ground, you could basically use the moon as a huge sort of antenna, and then use it as a diffraction edge kind of a thing. And then you could typically study the diffraction pattern as source went behind the moon and came out of them. Of course, like it's more like the moon going in front of the source, and moon like going in front of the source while occulting it, and then coming out, releasing it from its occultation and all that. But then for simplicity, I'm just going to explain it in a way where we see the moon as stationary and the source is like going behind. So then if we look at it this way, like when you have a radio source, when you have when you have an antenna whose beam is like much larger than the size of the moon, and you have a source, and in that case, the resolution of this system is decided by the distance between the Earth and the moon at the given point of time. So this would already give you like close to 8 arc seconds or so. And then depending on where the moon is, like I'm just giving a rough number based on Cyril Hazard's papers. But then like if you looked at a source which is going behind the moon, it would sort of like give a pattern like this, where you have this steep rise. So you have this. So the time is actually like going from right to left in this picture. So you have this high intensity that you are measuring from the source, but then as the source is hidden by the moon, you have this drop in the intensity, and then the next time when the source comes out, the intensity rises again. So by knowing how fast this intensity is dropping and rising, you would be able to find out what the angular size of the source is. But again, the problem is like not all sources come close to the moon at all the time, at all the places, and you can in principle do this from different places at different times. But it like once you want to do this for the whole sky, it sort of starts becoming infeasible to do this. So but then like the Ooty radio telescope in India, for example, was initially built to continue the study, and the study has like yielded a lot of interesting results. And for example, in Cyril Hazard's experiment, he had one dish from Jodrell Bank which was looking at the moon, but the Ooty radio telescope did it differently, where they had like 12 different beams projected on the moon along the right ascension axis, and then as the moon's path in the sky changed, they were able to make identifications of close to 300 sources or so, if I remember correctly. And then many of them, they were also able to like pinpoint their locations correctly, so that they matched with optical. They were matched with optical observations also, and they also found new optical counterparts for like previously unknown radio sources. So then, but then again, like we discussed in the previous slide, the limitations are that you can't do this every day for every source, and then when you want to survey the whole sky, it sort of becomes limiting. So one of the important problems that plagued the early radio astronomers were the structure of Cygnus A, because like once Bolton and even Bolton and Slee were able to find out the rough size of Cygnus, then the next question was how did the source look like? What was the source's structure like? Now we know that it is this it's a double source, like with two jets and a core in the center and all that. But then this was a question which had to be answered early on. And so this for this, like Robert Hanbury Brown and his colleagues Jennison and Dasgupta, Professor Dasgupta, like I think he was also the chair of the radio physics department at Calcutta University. So they came up with this interesting idea called the intensity interferometer, where instead of trying to do a phase coherent interferometry, you try to make a detection of the intensities from the receivers separately as possible, and then try to correlate the intensities. And this sort of gave you the fourth order correlation of the voltage signal itself of the electric field. So from this, you were able to find out approximately how the sources looked like and all that. But this sort of but then in the but then as we go to the future slightly, we would see that we do have ways in radio astronomy where you could in principle record the voltages directly and correlate them at a later point of time. So this was sort of ignored in favor of phase coherent interferometry in radio astronomy. But intensity interferometry itself is a big is still very effectively used in quantum optics and quantum communications, for example, where you have bunches of photons correlating, and you could like literally say the properties of the source using using the intensity correlations from them. But coming back, there was these two antennas which were separated at a certain distance. The second receiver here was movable, so you could like move it around wherever they want from England, which was restricted by the transmission link that you see here. The transmission link basically was a radio link where the recorded power was sent from one of the outrigger receivers or something, and that could be like correlated back inside. So and using this experiment, they were able to like initially find out this double source structure of Cygnus A, which was a big result at the time. And see here, like if you see, they measure the cross correlations of this at different points, different baseline lengths, and then based on how the shape of this cross correlation looks like, they are able to say how the shape of the source itself looks. There is a little bit about the theory of interferometry itself, which would come to at a slightly later point of time. But at this point, you could just what is important is that like if you know how the cross correlation between a particular spacing looks like, and you're able to construct this for a large number of spacings, you would be able to like infer how the source structure has to be, because there is a Fourier relation between them. And the first case of like phase coherent interferometry came because of Bernie Mills. Like so he had this 25 square meter Yagi antenna at one place, and he made this outrigger antennas, which is shown in this picture. Like you see two antennas mounted on a trailer, and this mast is actually the antenna which was used to transmit the local oscillator from the main site to the receiver site in general. So the block diagram of the system sort of looked like this. So where there was a radio link which was used to transmit both the local oscillator and also the radio signal itself received at a particular IF. And then this so this sort of acted like this phase coherent interferometer, but then the yellow was transmitted from one place to another place. So this is sort of like a connected element interferometer, but then the connection, instead of having coaxial cables, happens with an active radio link itself. And so from this, again, like he was able to derive like using coherent interferometry source structures of like different sources. And then similar experiments were carried out in England also, like where this is the precursor to the E Merlin array, which exists currently. So again, like here, they were able to like extend the baselines up to 115 kilometers, because they used a more powerful transmitting antenna, and this was like a more complete system in general. And they were able to measure fringes on sources up to 61,000 kilo lambda. And so here you see they also have to decode this diagram, like you have this portion which is basically the antenna that is stationary, and then you have this, which is the remote antenna. So if you see, actually there are like two things that they are transmitting. One is the local oscillator from one place, and then the other thing is actually the radio signal. So this antenna on the top is the one which is transmitting the local oscillator at 175 megahertz, and then this comes to this side, which is picked up by a receiving antenna, and then that is amplified and then mixed, and then again so you have this thing which is sort of like measuring the round trip phase also, and then you have also another local oscillator which is based on the signal from this, but then like you sort of measure the IF and then transmit that, which comes back to the correlator where you and then there is also this phase shifter which can compensate for the differences in the local oscillator signals on both the sides, and then so then like this they were able to like do similar measurements for 384 sources, which was first at that point of time at 150 megahertz, and most of these experiments happened at the low frequencies because like you had a larger signal to noise ratio to work with than at the higher frequencies, and this is the precursor to the E-Merlin that we have today, and which will take. But then like this happened slightly towards the end of the 1950s, and then in the 1960s a few advances happened in technology, where you had the first rubidium oscillators that were available for observations, and then you also had like first commercial computers that were available for labs to purchase, and you also had data recording systems, like where you could either record data in an analog way or in a digital way. And so the Soviets were the first to realize that, for example, without doing any retransmission or like having a radio link, it is possible to sort of measure. It is possible to measure and correlate and create interferometers between two different locations by recording the data on a tape. So this was at that point called tape record interferometry, and this was sort of what added the very to the long baseline interferometry name, because the long baseline interferometer itself, like when we saw, they were all having these radio links, active radio links, live radio links, which are again restrictive, because you need to have a very powerful transmitter if you had to like transmit signals to kilometer wavelengths, and then if you want to like transmit like huge bandwidths of data, then when you want to transmit high frequency waves, then you have like lower. You can't do it for a long distance because they get attenuated faster. So this was sort of a new idea that both Canadian radio astronomers and American radio astronomers were playing with. The Canadians were trying to do the recording in an analog sense, while the Americans were trying to do it in a digital sense. So this was a scheme of the first Canadian system that was there. So you could see the two tape recorders that they are using to record them, and the tape recorders were played back at the correlator, and they were correlated at different delays. And so they could find which delay yielded the maximum signal to noise ratio. And so this had, so you had this thing like where so they made a comparison with this initially in one of the I think it was probably in Algonquin Observatory, where they had two antennas placed close to each other, and they were able to like show that they had identical fringes when they when they were connected to the correlator directly, or when the recording was done with disconnected elements and correlated later. So this, and after this, they moved to larger distances, like of the order of even 6,000 kilometers, and eventually they were able to do with one telescope being in Canada and one in England, and they did a survey at 408 and 448 megahertz. But now we'll take a small detour into digital signal processing. So where you see, like I said, the Canadians used analog recording while the Americans used digital recording. So this, both have its own advantages. But then when you want to like sample a signal from analog to digital domain, you are basically doing two steps. One is you're trying to like measure what the signal's value was at particular timing instances, and this process is called sampling. And once you've done this sampling, you have to assign a value to each of the levels that you measured at different times, and this process is called quantization. So typically, like back in the early days, we did not have ADCs which could sample at 10 bits or 12 bits. So you just had to do sampling at 1 or 2 bits. So there were some early works on how, and if you want to, like, for example, say sample things at 1 bits, all you're doing is just like measuring the zero crossings. But if you want to do it at 2 bits, then maybe you could have like two levels, and typically 2-bit quantization would have like four levels in them. Like, so you could have like 0, 0, 0, 1, 1, 0, and 1, 1 levels. But then again, like, because now you're like truncating a large part of the signal, and you're just having access to partial information, quantizing at very low number of bits will give rise to more quantization noise. And this, for example, would sometimes limit the extent to which you could actually do correlation between the two samples. So here, for example, what you see is the cross correlation coefficient and the correlation coefficient of quantized data and how linear they are. So this, the bottommost curve that you see is what happens when you have 1 bit, because you just have noise that is clipped, and you don't really have any other information on the amplitude itself. But then when you like keep increasing the number of bits that you have access to, by the time you reach 4 bits, you're almost as close to the real analog correlated values itself. So this is one of the reasons why radio astronomy, like, people tend to use quantization levels as low as like 4 bits for connected element interferometer cases, because we want to like get to as large a bandwidth as possible. And typically, like for noise like signals, 4-bit quantization gives you almost correlations as close to doing it with an analog correlator. But still, many state of the art VLB experiments use only 2 bits, because in most cases 2 bits are and because in most cases they are required to store gigabytes of data. And 2 bits sort of like offers this with 2 bits you could already reach 86% of the cross correlation that you would be able to measure with an analog correlator. So there is sort of this trade-off, because like you have these real-time data links also, and you have like limitations in how fast you could record a signal to the disk and all that. And increasing the bandwidth increases your sensitivity also. But while increasing and this reduced quantization is just a small penalty to pay for it. And here what is shown here is the different levels of quantization, and beta here is the oversampling factor. So even with just 2 levels or a 1-bit quantizer, if you oversample things by a factor of 4, you would still get 78% or 80, close to like 80% of what you would get from analog correlator. But you see, like beyond a point, it starts saturating. So in principle, if you really want to get as close to possible, like 16 levels are like 4 bits. So here you see, like by the time you are just oversampling it by 2, you have already reached 99% of what you get in analog. And for 255 level quantization, like what an 8-bit ADC would offer, you have already like reached what would be offered to you by an analog system. So here again, like using this fact that you just need 1-bit quantizer to like reproduce things at a slightly lower SNR was used by the group in the US, and they came up with their first data recorder called the Mark 1 data recorder. So which used so here if you see, you that there was this the antenna's output was connected to a parametric amplifier which produced both side bands, and then they were actually like clipped by a comparator, like we saw here. And then they were recorded at 720 kilohertz on a magnetic tape, and then the tapes were like played with a delay line. So this is to the delay line was there so that they could like shift samples by a few. They could shift samples like by providing delays when they were processing the data, and then see if they actually like matched well. And then and they were able to like sort of figure out which delay gave them the maximum signal to noise ratio. And then that is the process of fringe finding, because like where you just like kept shifting things around and tried to find out which gave you the best signal to noise ratio, and that was when you have detected your fringe. And they had a software correlator implemented on a 360 by 50 IBM computer for the first time. And this is the process of fringe finding. As you see, like this was done probably at the minimum at -3 times the sampling rate to 1, and then like when the delays were like exactly matched, you got the maximum signal to noise ratio, and then like it diminished again like as you moved the sample further away from the delay that was giving you the maximum signal to noise ratio. So now if we like analyze the response of the interferometer itself, like this is what a typical interferometer would give. Like you would have two components. One is the real component of the fringe, and the other one is the phase shifted imaginary component of the fringe. and the wavelength is and this is dependent on the wavelength of operation. And then d sine theta is actually so the 2 pi by lambda d sine theta is actually the path difference between the two interferometers, and this arises as a consequence of the fact that you have a finite spacing or a baseline between them. So then like you could just measure one component and get only amplitude information, but then you could shift them by 90 degrees to get like a real fringe and an imaginary fringe, which can then be used to uh, create a complex visibility. And then so here if you see this 2 pi by lambda d sine theta component has both the geometric phase and the source phase. So the process of removing the effect of the geometric phase out of this contribution is called the fringe stopping. And most interferometers that are operating in real time also do this, where the the source is positioned accurately, and you know that what geometric delay or phase it would cause on an interferometer of particular baseline, and remove its contribution, so you get access to the visibility phase directly. And then so now if you had like multiple antennas in an interferometer like this, and each of this, and depending on the spacing between them, you would have a product and your total visibility would be a sum of the visibilities that you measure in individual baselines, right? So, and now if you actually like write this, so each baseline is now 2 pi by lambda d sin theta is sort of what is measured by one baseline, and the second baseline would have a slightly different, the third one will have a different value. And so if you like write it in terms of a complex exponential, you would realize that it is actually the brightness that you get from the source is actually only the inverse FFT of the visibility. So this is what the whole process of like interferometry boils down to. So all you need to do is like measure visibilities and then do an inverse FFT to get the brightness distribution. Of course, like you have to do a lot more steps in between, like where you try to remove the effect of the instrument and all that. But then it is possible. But then like basically it just like, but given that you have an ideal instrument with no noise and everything, ideally this step should give you the brightness distribution directly. So this was realized first by and then now, for example, if you had these antennas which were rotating on the surface of the Earth, so each time it rotated, the baseline separation as seen by the source would change. And this sort of like gave you, so like if you had the two antennas that are separated at a distance of like 10 meters or so, depending on the position, depending on the relative position that the baseline vector was obtaining with respect to the source, and as the Earth rotated, you would have slightly different baseline lengths. And if you had more antennas like this, you would be eventually able to like create an artificial aperture which gets filled. So this is what is called as the UV plane filling and all that. And then and this is what is called the Earth rotation aperture synthesis also, which many telescopes like VLA, GMRT, etc. use to create images. That's like images from like very nice high dynamic range images, even from just like 8 hours of observations or so, like, or even less sometimes, given how compact how many antennas the interferometers have, and how are they arranged and all that. And so once you have made these measurements from different projected baselines and different antenna spacing, etc., you can then in principle invert it to get the source brightness distribution. And Sir Martin Ryle was awarded the Nobel Prize for initially finding this. And this is a principle which is not only being used in radio astronomy, but also like it is being used in areas like MRI scans and all that. So now again, and then another thing that was here is like, okay, now we have measured the visibility phase, but how do we separate the phase of the instrument from the phase of the source itself? So this is done by this principle called closure phase, where if you had like three baselines measuring radiation from a particular source, you would be able to like remove the baseline contributions and the individual antenna contributions by defining this quantity called as closure phase. Like if you had 4 antennas, you would have 3 closure phases and 1 closure amplitude. And so these are in principle like used to remove the effect of the antenna itself on the signal chain. And the discovery of these two are like crucial to the establishment of long-term VLBA networks. Like for example, today, because this and due to self-calibration and also availability of cheap computers, etc., you are able to do VLBA almost like as you would do a normal interferometric observations. And this was realized, and soon a lot of networks were built to do VLBA, dedicated networks. So for example, VLBA in the US, very long baseline array, is such a dedicated network. And then in Europe, Europe has got the European VLBA network, which is an array of heterogeneous antennas. So the antennas are like different, but while in the VLBA, all the antennas are identical and the receivers are identical. But then different telescopes, which are like built for different purposes, take part as a part of the European VLBA network. And then there is also an East Asian VLBA network, which is made out of Chinese, Japanese, and Korean VLBA antennas. And you also have the global millimeter wave VLBA array, which was sort of a precursor for the Event Horizon telescope itself. And some telescopes from the global millimeter wave VLBA array also regularly participate in Event Horizon telescope measurement. And they also had space VLBA, like one of this was called the Halka, which was built by the Japanese early on. And then there was this other experiment called as Radio Astronomy, which was built by the Russians, and they also like produced significant results. So another area in which VLBA is very applicable, very useful is geodesy. So where so here the question is asked in a reverse sense. So given that you know position of like a set of sources in the sky, which you know is not varying too much in the span in which you are observing, can you use this information to sort of find out how the how for example the Earth's parameters have changed, given that you know the source, everything else is constant. So the main observable here is actually the group delay, and and you have like a set of sources, close to 200 sources or so, which are being observed regularly for these geodetic VLB observations. These are sources like whose position we know up to a very good level of accuracy and know that they don't change too much over a year. And here again, we will take a small detour to like understand this concept called as bandwidth synthesis. So as you know, there is a relationship between phase and delay. So delay is actually 1/2 pi, and phase difference at two different frequencies. So delta phi by delta f. So the idea is like if you are able to measure phase at frequencies that are separated widely from each other, then you would be able to make a more accurate phase determination. And this is called as bandwidth synthesis. And this is what VLB experiments use. Geodetic VLB experiments use also. And then so here, if you see the delay can be like split into different components, and this is a sort of a small electronic system which creates pulses which can be fed in close to the antenna or even the feed itself, and this measures the phase difference or the phase variations that is added by the analog chain itself. And there are ways to like model the ionospheric, tropospheric delays. So many observatories which they are observing in the millimeter wavelengths have this thing called as a water vapor radiometer, which measures the column density of water vapor and tries to find out what the delay is. And you can get ionospheric delays by using GPS measurements or sometimes even direct measurements of the ionosphere. And then like when for example like you have spacecrafts, for example, you also have a relativistic correction that you have to make, because when you have two antennas that are separated by very long distance, so wave one has reached antenna one, but then wave two has not yet reached the second antenna. But then by the time wave one reaches the second antenna, wave two has been incident on the first antenna. So this sort of like creates this Doppler delay between the two antennas, which also has to be corrected. And this is the relativistic delay component of this thing. And so this is a schematic of how you could like do this delay measurement at different frequencies, and how also it is being used by geodetic VLBA. So typically like geodetic VLBA observations use S-band and X-band. But then like now S-band has got a lot of RFI because of a lot of new satellites that were launched. So the new specification defines a total span bandwidth of like 2 to 14 gigahertz, and this is defined by the more latest VLBA for geodesy specifications. And the measurable here, like again, when you have like multiple bases, that like you have like fringe rate and fringe frequency, delay and rate is what you would typically measure. And so when you have a fringe that is detected, you would have a high signal to noise ratio at the delay and the fringe rate that is corresponding to your particular thing. If you have in principle taken care of like all other effects which are like variable, you would typically like get a fringe match at zero phase delay and all that. So but then it depends on a lot of other stuff also. So another thing is like, given that we are trying to record voltages at different antennas separately, an important role in this experiments are played by the type of the clock you use. So you can't simply take a quartz oscillator and wire it, because that the frequency variation in the output provided by a quartz oscillator is sometimes too much, that it sort of like washes out. It is not sampling the voltages at two places coherently anymore. So this early on this was realized, and atomic oscillators like rubidium standards or hydrogen masers were initially used. So this plot here shows you how the phase was measured between different baselines of an interferometer, which was interferometer between Haystack Observatory and then Naval Research Laboratory in NRAO. So here, if you see the baseline between NRAO actually at that point of time had only a rubidium standard, and so here you can actually see how the standard, how the Allen deviation between different sample look like. So Allen deviation is actually the 2-point standard deviation. So if you had a time series like this and you made a straight line connecting A and B, the deviation of the second point between the first and the third points mean is the Allen deviation. So you do it again like for, so this defines like how good a clock or how stable a reference oscillator is. And so the lower the value, the more stable it is. So if you see for hydrogen maser and then cesium fountain, or even like hydrogen maser 2012, it has like stability Allen deviation of the order of 10 to the power of minus 14 seconds per second or so. So this, so the lower the plot traces in this curve, the more stable it is. So here you see rubidium is actually somewhere on the top because of this. Like for baselines where Haystack was correlated with NRAO or NRL was correlated with NRAO, you had like very bad phase variations, which was mostly because rubidium oscillator was used instead of cesium. But then the thing is, like, not everyone can also afford a hydrogen maser. So so it also depends strongly on the frequency that which you want to do this observation. So like when you're probably observing at frequencies as close as 1 gigahertz, you could probably afford to have a slightly cheaper clock, and you don't necessarily need to have a hydrogen maser or so. But then like when you want to go close to like a few terahertz or something, you could see that even a hydrogen maser is not very good at producing the full coherence close to like 1. So but more recently technology is like advanced slightly, like where you could generate an optical comb and then transmit optical transmit signals from an optical link to different antennas around. And this was demonstrated by an experiment conducted by the Italians, and they were able to detect fringes in real time when this clock was transmitted from one place from one of their stations to another stations. And they were also able to like show some results between Germany and Italy also. So, but this has not become mainstream yet because there are like restrictions regarding the availability of the optical network from like different places, and then the standard of them and all that. So this was a one-off experiment, but then maybe you would get there at some point of time in the future. And then regarding the receivers itself, like you have like this is a diagram that I've taken from the Event Horizon Telescope receiver. So I will mostly speak about at low frequencies it is only mostly dipoles, but at high frequencies, for example, like when you operate the millimeter wave wavelengths, for example, you have these special components called as the SIS mixers, where the radiation is directly like made to fall on the RF port of the mixer directly. And so typically when you look at any RF chain, the noise added by the chain typically depends on the first element of the chain. So in most cases, people try to have it as a low noise amplifier so that their receiving system itself adds as low a noise as possible. But then this is not possible in the millimeter wavelengths because you don't really have low noise amplifiers that can operate at such high frequencies. And because of this, like the first stage is typically an RF mixer, and these mixers are typically like cooled cryogenically, so they operate at 4 Kelvin or so in temperature. And then because you also need to get as high sensitivity as possible, double sideband separating mixers are typically used. So you have like access to both the upper sideband and the lower sideband. And and like in the previous estimation of delay, like we saw that once you have taken care of all the other delays that you are able to model, the only uncertainty that would still remain is typically the atmospheric contribution. And this is sort of cancelled out by making measurements using water vapor radiometers currently. But then the water vapor radiometers usually have a different optical path compared to like what goes on in your receiver. Sometimes this is seen as a limitation when you want to make very high dynamic VLB observations. So a new area which we are investigating here at Onsala and at many other observatories are 3-band receivers, like where you have where you have like almost the same optical path for three different bands, and you can sort of like do a wide bandwidth delay estimation using the correlations received from these three bandwidths. So this is an active area of research that is going on in terms of as far as front ends are concerned. And then in terms of the back ends, there is interest always to like keep increasing the band that you are able to sample as much as possible. But then currently, like there are two standards that are being used by VLBA and then the EVN. The EVN uses this thing called as a digital baseband converter, or the DBBCs, while Roach based solution is more used for the VLBA based systems. But then these two systems are being now upgraded to enable them to like sample at least IFs of 16 gigahertz or so. And we at Onsala are also working on trying to use modern radio frequency system on chips, for example, to see if we are able to like increase this bandwidth further. And in terms of correlators, initially like ASIC chips, application-specific integrated circuit chips, were used to implement cross correlations, like both FX and XF correlations. But then these days it is mostly FX correlator that is being used. The advantage being that an FX correlator gives you better signal-to-noise ratio on a per-channel basis than an XF correlator. And then like you have this. But then these days, like it is being implemented mostly in software and then using GPUs. And one of the most famous implementation of this is the TFX correlator, which is sort of become the de facto standard for most of the VLB observations that are going on. And it is also like very flexible, because like adding a new receiver or a format to it is just a matter of writing a new module in principle. So then like we would take a detour, like for example, on seeing how this has been going on in India. For example, I'll start off with something which happened more recently when we were doing when I was doing my PhD work. So we tried to do this solar long baseline interferometry between at 38 megahertz, which at that time was one of the firsts to do this. And then we were able to like use these experiments to find out source sizes in sun as small as 15 arc seconds or so. And this was a big deal because in the sun, many people through modeling had shown that like it would not be possible to like observe these sources of small angular sizes, mostly because there is too much of scattering going on in the sun due to the fluctuations in the plasma densities itself. And this sort of limits the maximum size that you can see observed from the sun. But then we proved this other ways, and after this, like there have been much more many more observations using the GMRT, where they have shown that it is possible to like observe sources much smaller than almost an arc minute or so. And then like another thing is that localizing FRBs using VLBA, like we have been speaking about this fast radio bursts in the past few years, and there have been many telescopes which are being built to effectively like localize them. And so we were also working on this project. When I was working in for the HIRAX project, we were working on this special project where we were doing the study on seeing like how to add more antennas through in the all of South Africa, to see if you'd be able to like synthesize sufficient angular resolution and sensitivity and aperture that was sensitive, and also had sufficient angular resolution to image these FRBs in real time, as we had a trigger from the main station. This was something which is based on that. But and this array is still being under construction, so maybe we would start expecting to see results in maybe a couple of years time or so. And then another thing is like we said, like in Onsala here, like we are trying to build a new 3-band receiver, and this 3-band receiver would simultaneously observe at K, Q, and W band, so we can make a better estimation of the atmospheric delays, and then add to the dynamic range of like the images that you are able to produce from this. And there are also like VLBA projects in India. Like one, for example, is Swan, which is a project by Avinash Deshpande, like he's now at IIT Kanpur. So the idea here is to like have these tiles of dipole taken to different universities all over India, and then try to make all sky images, and then also see if you're able to take transients and all that. And a lot of people like who worked on this project were also like working on their PhDs abroad and all that. So, and this also like has given people a lot of hands-on experience on developing instrumentation for radio astronomy, and understanding how antennas and arrays work. Another project that is being spoken about now is this geodesy project called Project Saptarishi, which plans to establish its own space geodesy center in India, for example. But in the past, I think like even before our experiments at Gauribindur were conducted, there were VLBA experiments between Ooty and antennas in the European Union as old as 1989, and there are some, yeah. So there have been some very interesting results from these experiments also. But more significantly, like I have just tried to like limit the results to like this three that is showed here on the interest of time, which I think I've already exceeded. But so then you have this. So some of the significant results were like for the first time, VLBA was used to find an apparent superluminal motion, and this could only happen because the source was traveling towards you. So things got blue shifted that it appeared as if it was traveling many times faster than the speed of light. And then the second one is actually like the more recent result, which was the images of the black hole, which mind you was actually the largest angular resolution that any telescope could produce at any till date, which was approximately 25 microarcans or something, and which like many optical telescopes or like telescopes in other wavelength are not able to produce as yet. And on the extreme right, you see the displacement of baselines when there was a huge earthquake in Chile, I think, for example, and this was determined by VLBA and GPS measurements, and this was a significant result on showing like how VLBA products are indeed useful for geodetic VLBA geodesy applications also, and these are very important because because the Earth orientation parameters are regularly used by satellites or space agencies during satellite launches and all that. So yeah, and in terms of the future, there are a lot of small experiments on balloon-borne VLBA experiments for millimeter waves and all that. And then the people have also been speaking about this extended event horizon telescopes, where they would have like a larger number of antennas distributed all over the world to increase the coverage of increase the spatial frequency coverage of the basic event horizon telescope. And there is also plans to have a millimeter wave telescope at Hanle in India also. And then there is also like talks of event horizon telescope having an extension into space, where you would have an orbiting satellite which would be used to correlate their signal from between the antennas on Earth, and then see if they are and then simulations, so that like you are actually able to like resolve more into the structure when you add a baseline in this baseline in space. So I think it is going to be like exciting times in the future for from both like geodesy and as well as astronomy perspective. But most of this also would come with development in wideband feeds and high speed digitizers, and also like develop more innovative optics, so that like it is possible to observe more frequency bands simultaneously and have multiple band receivers. And then also like the infrastructure for transmitting data between one VLBA station to another VLBA station gets into this domain of like the whole new politics and other involvement between multiple parties, which has sort of not caught up to the way in which you are able to like you are able to record data at a much faster rate than you are able to transmit it for correlation currently. But hopefully this would change in the future once you have like better modes of communication between different places. And then it would also be interesting to see if the clocks are being distributed in real time. Then that would also like eliminate the need for having very costly uh, reference clocks, and this sort of would make uh, it easier for newer research groups to enter into VLBA development in general. So I guess that brings me to the end of my talk. And I saw a lot of questions go up, but I'm not able to see the chat now. So if someone can read it, I can answer it. But yeah, thank you.
Thank you, sir.
You are muted again, I think.
Oh, sorry. Yeah. So, yeah. So basically, thank you so much for the talk. And now we'll be opening our panel for questions. So if anyone has any questions, please drop it in the message box, or you can unmute yourself or raise your hand. So I'll read out the questions. We have a couple questions in the chat box. So Aruna asked that, so can we make antennas for any EM spectrum region, or is there any limitations where we cannot make for a particular spectrum region of the EM waves?
Um, yeah, you could like make antennas for any frequencies. Like there are also like some people that have been doing research on antennas for visible wavelengths also. So, but it's mostly a problem of like how efficient that antenna would be. So yeah, but I guess it is possible to, like, even if you had your normal FM antennas, for example, you would be able to still tune into higher frequencies and listen to things from there. But it is mostly the matter of like how efficient would the antenna be and how would you be able to like increase its gain in a specific direction and all that. Yeah.
Okay. Okay. Next question is from Dev Jyoti. He wanted to ask about some paper of yours. Dev Jyoti, would you want to unmute your mic and ask it yourself?
Hello, Dr. Mugundhan.
I
Yeah, I am a undergrad student at Tezpur University. So I want to ask about a paper about related to like high performance computing for FK transient search. You have published it, like I have searched about it, and
Mhm.
so I just
Yeah,
want to ask something. Do you still do some work on FPGAs and high performance computing or something like that?
I still work on FPGAs and digital receivers, yes, but not so much on the high performance computing aspect.
Okay, like I am very much interested in that particular domain, so that's why I'm
Mhm.
asking about you. Like I am asking
Oh,
about you. So
yeah.
so like
I do work on the FPGA side of things, but not on the high performance computing yet. Yeah, so
but if you like, I just want to ask like if I like I if you have some vacancies or like if you take some students, then I can actually work with you in this particular domain. I have some
maybe
experience with FPGA programming and
okay,
FPGA.
maybe we can discuss this over a mail.
Okay, I will send you a mail.
Mm. Yeah, okay, thank you.
Okay, so thank you, Devjit. The next question is from Sonia. She has asked that does the choice of quantization bits and the resulting quantization noise might vary depending on the specific scientific application or use case?
Yes. It would depend on like what science or use case that you want to like. Typically, for example, like if we took for example solar radio observations, like the bursts from the sun are maybe 3 to 4 orders of magnitude stronger than the background itself. In which case, you need more dynamic range. And then when you are recording things with more dynamic range, this automatically translates to like having a larger number of bits, so your signals don't clip when you are recording them. But then in terms of VLBA, where you are observing sources which are not expected to burst out, you would in principle like to have as low bits as possible, because then you can increase your bandwidth. So if typically like if you had a 100 gigabit Ethernet link or something, you can only uh, transmit, for example, like if you transmit like just 1 bit signals, you can increase your bandwidth in principle up to 100 gigahertz, right? But then like if
Mm.
you use 2 bits, you're reducing it to like 50 gigahertz already, and then it scales on like that. So it depends on the science. Definitely, I have seen in cases like where very strong FRBs have been clipped because the digitizer had only 2 bits, and this led to some problems in correlation. But also in VLBA, people typically like escape with a lot of, like, even if you had a lot of RFA in your local station, it is possible that the same RFA is not present in the remote in the station with which you are correlating your signal also. So this, because the signals are not correlated, they get suppressed. So this already gives you some level of filtering. So you are in principle able to like escape with lower number of bits for correlation. So yeah, it does depend definitely on what it
Mhm.
is used for.
Okay. So next question from Shayonjeet. What is frequency stability and how it's been calculated, and what it actually represents in the final result in VLBI?
Yeah, okay. So like your interferometer is finally measuring amplitude and as well as phase correlations between the signals that you are receiving at two antennas, right? So in principle, like, yeah, when you want to correlate two signals, the assumption is that they are also being sampled in a way that is phase coherent, which means like if I'm sampling something at time instant one in one antenna, I expect that the same voltage will be present at the second antenna also at the same time instant that I'm sampling. But now if you had oscillators where your the output, like let's say for example you have an oscillator which is like very bad in accuracy, that when you connect it to a spectrum analyzer, you actually see it at 10 megahertz, but then the next instant when you want to like average and measure it, it actually is at 10.1 megahertz or 9.8 megahertz or something. So now your oscillator's phase is fluctuating a lot, which means when I'm sampling my the voltage that I have from these antennas, I'm not sampling everything exactly at 10 megahertz, but there is like the small oscillation or fluctuation in my sampling interval. So this leads to like the signals not being sampled at the right instance, and when you are in principle and so now when you are correlating things, and your correlation coefficient finally depends on the delay between the two antennas. This would also in principle this would then sort of like add noise to the original geometric delay that you want to, the original delay from the source that you want to measure. So that's why it's like in principle better to like minimize this noise due to the instabilities in the frequency source that you are using. So yeah.
Okay.
So typically frequency
So
stability is a parameter that is used to like quantify this is called as phase noise or and Allen variance. Yeah.
yes, yes, yes. So another question from Sonia. What are the main differences in signal processing approaches between real-time VLBI and traditional post-processed VLBI? And second part, how do these differences impact the final scientific output?
Mhm. I think there are not much differences in terms of signal processing itself. Like it would the flow would be the same. For example, like you would have to still delay the signals. You would have to stop the fringes in real time. You would have to search over a delay space in real time and all that. So, but the only places where this would impact things in a real time is that when you want to do the correlation in real time, you have like very limited time to do all these things. But while you're doing an offline processing, it is much more easier to, like for example, if you are doing this in real time, then the number of delays that you typically search for would be much lesser than when you are doing it offline, because then you can search for a larger delay and bandwidth space to find where the fringes are. So and I think but the most important restriction comes from the fact that you can't really have real time links all the time. For example, EVN has like one EVLBA session for a whole observing season. So yeah, and that is mostly because many people don't have the infrastructure in place to transmit signals in real time.
Hmm. Okay, so next question is Sonia Zatlin asked that how calibration of VLBI antennas take place, especially for large areas with diverse antenna designs and geographical locations.
Hmm. Okay, so there are like multiple levels of calibration. So one level of calibration is using the pCal tones themselves, like where you inject tones to the whole signal chain to find out how the response of the gain and the phase response of the signal chain is varying, and that would be factored in when the main calibration is being done. And otherwise, like it just uses calibrator sources, like how normal how you do it in normal interferometry. So as there is not much difference between traditional radio interferometry and VLBI, other than the fact that your antennas are disconnected. So, but otherwise the steps are all the same.
All right. Shayanjit has
And
asked,
then of course, sorry,
yeah, yeah,
and then of course, like one additional thing is that like depending on what frequency you're observing, you need to typically measure what goes on in the ionosphere at your location or the
mm,
atmosphere at the location, and factor
right,
that
right.
so that your delay can be modeled accurately. Yeah.
Okay. Shayanjit has asked 100 gigabit Ethernet is for what? Shayanjit, would you like to
It is
do?
to. Mhm.
Yeah.
Okay, it is to record the data and then like to transmit the data from your VLBA station to the correlator, the place where the correlator is in. Because at this point there are only like three places where VLBA correlation is carried out.
Mm,
One is at Germany and one is at Haystack and maybe at and there is also one at Aston and Jive. So most VLBA arrays ship their data in disks or something to these stations, and when EVLBA happens, like the data is transmitted over a very small bandwidth to these stations to do this in live. But then, like when you have a larger bandwidth connection to go from one place to another, like the 100G Ethernet or something, for example, you have the scope to like transmit larger bandwidths in general and record larger bandwidths also. Yeah.
all right. So if anyone has any more questions, please unmute your mic and ask them, or you can also drop it in the comment box if you want. All right. I think there are no more. Okay, so one more question. What kind of data compression techniques are most effective for reducing the data rate in VLBI?
Mm, the signal that we are looking at is mostly noise lake, right? So there is not much you can most compression algorithms relies on the fact that like you have some patterns in the signal, and if you just are able to effectively capture that pattern, you'd be able to like represent the signal as much as possible. But then when your signal is very random, there is not much you can compress already. And maybe what yeah, yeah. So if at all like you want to do some compression, you can't do it on the raw data itself, because that is what is deciding the data rate in VLB, right? The data at which like you're recording the voltages directly. But then once you have like cross correlated them or made them as images, then you have like a larger scope to compress them. But then if you want to like compress the raw voltage itself, there is not much you can do.
Okay. If there are
Hello, sir.
not, yeah.
Yeah. Sir, like you have just explained about that compression techniques in BLBI. So, like you have said that the signals are already there are a lot of noises. So, like whether we use a compression technique or not. Uh, but the thing is, we can pass through the signal. Like we can reduce the noise using some mathematical models. Like we can use like MPDR algorithm. Like there are some mathematical
Oh,
models to reduce the noise power at the output, so that after that we can compress the signal. Like
no, but this is not noise in the sense like the signal that we want to measure itself is noise like I said in one of the earlier slides. That is because the signal that you receive from the sky itself resembles that of Gaussian noise. The statistics of the signal is like Gaussian noise. So the signal is also like not deterministic, and the samples but then and one sample that you measure at time instant one is not correlated to the next time instant. So then because there is no correlation between like different, the signal is in the signal is like stationary. It's not a non-stationary signal. And so if you have a signal which is just like has got no correlation between one time instant to the other time instant, you can't do much to compress it.
okay, okay, thanks.
Okay. Any more questions, or if anyone wants to ask anything, you can please unmute yourself. Okay. One more question. Given the massive data volumes generated in VLBI, what are the current strategies for data storage, and how do you address the challenges of storing such large data set while maintaining accessibility?
Currently, I think they are being stored in these huge disks, and then after correlation, I I think it's only the final visibilities that people usually get, because otherwise the data is like completely massive, and the disks are probably still archived and had. But then like if you want to like archive the raw voltages, there is probably like you would run out of space very soon. So I think there are some compression techniques that people are working on. So like you could use the visibilities, for example, or throwing away baselines like which have identical spacing or some things like that. But there is not much done, and maybe and I think what is being finally archived are also images and calibrated visibilities rather than the raw voltage itself. So you can't like really archive the raw voltages, but once you have like done some level of processing, then maybe it is a little bit more easier to store things. Yeah.
Okay. Um, any more questions? All right. Okay, one more question. What is your opinion on the FFT correlators that people are exploring for radio interferometry in the context of the LPI?
What FFT correlators are we speaking about? Are you speaking
Uh,
about the direct FFT technique for imaging that they are using, or?
yes, she says yes.
Mhm. Yeah, I think I don't know like if in VLBA itself like people are really interested in doing that, because mind you in VLBA like you don't really have so many antennas that you have to correlate. It is more a problem of seeing like how much of it can be done in real time. So I think while doing this like taking individual fields, doing an FFT of it, and then getting it into image would work in principle. But then for VLBA, I think like you don't have so many antennas in the first place to use a technique like that. That would like work mostly in case like where you have like a large number of antennas, large n antennas, and where like for example when you want to do a cross correlation itself, you have to do n into n minus 1 by 2 products. But then like if you had n antennas, and then if you use that technique like where you are Fourier transforming each antenna and then gridding them and forming images, then that would bring down the number of steps that you need for your computation. But for VLBA itself, like you are not doing so much. But maybe like if for example like you would want to do VLBA with phased array feeds or something, at that point it may be more useful. But it would still, I don't see that being like so useful to VLBA at this point of time.
Okay.
Because there is
Any
no
more?
use case in VLBA for that kind of a thing. Yeah.
Okay. Okay. All right. If there are no more questions, we'll be wrapping it up.
Yeah.
All right.
Thank you.
So,
Thank you.
yeah, thank you so much, sir, for coming to our talk. And I think everyone had a wonderful time learning about VLBI history, engineering, and its future prospects. And yeah, thank you everyone for joining in. See you next Astronomy Sunday events.
Thank you. Yeah. Bye.
Bye.